video, we're going to look at the section 10.1 and 10.2 notes. So in chapter 10, we're going to start talking about hypothesis testing. And so just like when we talked about confidence intervals, we revisited a lot of those ideas from your intro stat course, and we saw where a lot of those results came from. We're going to be doing the same thing with hypothesis testing. And so we're going to start with just a little bit of a review of what a hypothesis test is. So as you well know, a hypothesis test is another type of statistical inference. In other words, it gives us a way to take the information contained in a sample to say something reasonable about what's happening in the population. So whenever we perform a hypothesis test, we have what we call the research hypothesis, and that's what we want to show to be true. This is also known as the alternative hypothesis. So remember, in a hypothesis test, we assume that the null hypothesis is true, and then we see if the sample has enough evidence in it to prove or to conclude the alternative with some reasonable amount of error. And so the idea is we collect data and we examine it to see if it gives us that evidence to prove the alternative. And if the data is highly unlikely, unless the research hypothesis is true, we conclude that the research hypothesis is true. So in other words, this is where we use that p-value, and you used to say, if the p-value is low, you're going to reject HO, and that's because the p-value is low when we have a lot of evidence. And so for most of this chapter, we're going to look at hypothesis tests that are related to the confidence intervals that we derived in chapter 8. And then in section 10.10, we're going to learn how to use what's called the Neyman-Pearson lemma, and what that is it's a procedure for developing tests that are powerful. So we're going to start out in section 10.2 and just look at some elements of a statistical test. And so again, remember that we want to show that the research or the alternative hypothesis is true. And then the opposite of that, that's what we call the null hypothesis. And so it's the presently accepted hypothesis. In other words, it's the status quo. It's what we assume to be true. So for example, in 1492, Christopher Columbus claimed that the Earth was round, not flat. We could state the null and alternative hypothesis here. So notice that he makes this claim that the Earth is round. So in other words, that is the research question. That's what he's trying to prove. So we would say that the alternative hypothesis in this case is that the Earth is round. And again, this is our research hypothesis. It's what we want to prove to be true. And then the null is always going to be the opposite of that. And so in this case, it would be that the Earth is flat. Now, typically we identify the alternative hypothesis first because it is our research question, is what we're trying to prove. But notationally, when we write out the null and the alternative, the null is listed first and the alternative is usually written second. And then usually these hypotheses are going to involve the values of the parameter. You can think of them as they are what I am trying to prove about the population, but we're going to use sample information to assess that claim. And so another example that we have here is, what is the average height of a modern American man? According to the website, which is listed here in the notes, the average height for an early 17th century English man was approximately 176 centimeters. For 17th century English women, it was about 181 centimeters. And while average heights in England remained virtually unchanged in the 17th and 18th centuries, American colonists grew taller. And so averages for modern Americans are just over 183 centimeters for men and about 168 for women. And so the main reason for this difference is improved nutrition, notably increased consumptions of meat and milk and antibiotics. So suppose we believe that the average height of American male CEOs is larger than 5 foot 9 inches. To perform a hypothesis test, we could have the following. So we could use our notation that we have, for example, mu, and we could let mu denote that average height of American male CEOs. All right. So we're using mu to denote a parameter, and remember that our hypotheses are going to be in terms of the parameters. So I'm going to identify the alternative first, and notice what we're going to try to prove is we're going to try to prove that mu is larger than 5'9". And alternatively, I could have written this in terms of centimeters. And then the null is going to be the opposite of that. Now, when we talk about the null in words, we would probably say less than or equal to 5'9". You could write it that way, or we often will just write the equal sign. And it ends up that mathematically it means the exact same thing. All right. So next, suppose we take a random sample of 10 male CEOs and we find that the sample mean y bar is equal to 6'2". So the question is, would you conclude that the alternative hypothesis is true? And so we want to be very careful here because remember your hypotheses are in terms of mu, which is the population. We have information here about y bar, which is from the sample. Just because we see something in the sample doesn't necessarily mean that exact same thing is happening in the population. Now, in this particular case, our sample mean is much larger than our population mean that we're interested in. So in other words, it falls fairly far into the alternative. So in this case, we would probably conclude that the alternative hypothesis is true. Alright, so again, we would probably conclude the alternative in this case because if we assume that the null, if we assume under the null that the population mean really is 5'9", then it would be unlikely that we would observe a sample mean of 6'2". On the other hand, suppose that we took a random sample of 10 male CEOs and we observed 5'10". Now notice that 5'10" is not very far into the alternative hypothesis. And so the question is, would you conclude that the alternative hypothesis is true? Well, in this case, notice that yes, we are greater than that 5'9", but we're not that much greater. And due to sampling variability, I wouldn't be that surprised if mu really is equal to 5'9", and I observe a sample mean of 5'10". That wouldn't seem unlikely to happen. So in this case, the answer is probably not. And so for this example, we use the test statistic y bar to make our decision. And the idea here is we want to find a value c such that the alternative is true if y bar is greater than or equal to c, and where y bar greater than or equal to c is called our rejection region. So previously in your intro stat classes, you focused on using p-values to conclude hypothesis tests. This is another way to do that, and as we talk about this, I'll show you that it's really the same idea. And so what we could do is we can consider the following rejection region. We're going to reject the null hypothesis if y bar is greater than 5'11", Then if we take random samples of 10 males and observe that y bar is equal to 6'2", we would reject. However, if we take a random sample of 10 males and observe that y bar is equal to 5'10", we would not reject. So notice in the first case we're greater than the cutoff, in the second case we're not. And so here are these elements of a statistical test. So you set up your null and alternative hypothesis, you find your test statistic, and then you compare that to the rejection region. Now steps 1, 2, and 3 are exactly the same as what you've seen before with hypothesis test. This rejection region is the new piece. And it ends up that this step right here is just an alternative method to p-values. And I just want to talk very briefly why this ends up being the exact same thing. So previously, when you learned about p-values, what you saw you were doing was comparing the test statistic to the sampling distribution, assuming that the null hypothesis is true. And so the idea is if you have the sampling distribution, assuming HO is true, and I'm going to do this for a z-test statistic, but you can do something very similar for any other test statistic that you've worked with. If we worked with the z-test statistic, we know that it would be centered at 0, assuming that under the null being true, because you make that conversion. And so the idea previously is what you would do is you would set alpha equals to, let's say, 0.05. So if alpha was equal to 0.05, what you're really saying is in the tail of the distribution, if this were a right-tailed test, you're putting 5% of the area in the tail. If your p-value is less than 0.05, what that really means is you've got an endpoint that's over here, which results in, again, that p-value being less than 0.05. So kind of drawing on my picture here, if your test statistic was here, you would end up with a p-value less than the 0.05 area. The rejection region does the same thing, but instead of comparing the areas under the curve, it looks at the endpoints. So what the rejection region is doing is it's saying, okay, let C be here, the endpoint that corresponds to area 0.05 in the tail. If you end up with a cutoff point that is greater than C, you would have a p-value less than 0.05. If you end up with a cutoff that is less than the rejection region, then you're going to have a big p-value. So it ends up being the exact same thing. You're going to get the exact same conclusion whether you use the p-value method or you use the rejection region method. And then, as always with the hypothesis test, when we perform the hypothesis test, we're sometimes going to make errors. And so we've got some definitions here. Recall that we make a type 1 error when we reject H0, when H0 is really true, and a type 2 when we accept or fail to reject the null when really the alternative is true. And I do want to be careful here because we really don't want to say accept the null. This is really fail to reject. And then we let alpha be equal to the probability of a type 1 and beta equal to the probability of a type 2. Now, you've probably seen this comparison before, but remember, hypothesis tests can always be compared to a trial. And so, for example, in the judicial system in the United States, a person is innocent until proven guilty. So we could state the null and alternative hypothesis and define our two types of errors in terms of this example. So our null in this case, since we assume that the person is innocent, is going to be the person is innocent. And under the alternative, we're going to try to collect evidence to prove that the person is guilty. And then we could define our two different types of errors. And so notice alpha is going to be equal to the probability that we conclude that a person is guilty when they are really innocent. Whereas the beta, or the probability of the type 2 error, would happen or occurs, right, or is equal to the probability that we conclude the person is innocent or really the jury comes back and says not guilty when they are really guilty. All right, so we can continue our example. So again, suppose that we want to test if the average height of American male CEOs is larger than 5'9", and we're going to use the rejection region of Y bar greater than or equal to 5'11". And then we're going to assume that we have a random sample of 10 American male CEOs from a normal population with variance 9. So let's kind of draw a picture of what the sampling distribution looks like, assuming that the null hypothesis is true. Now I'm going to do this before the conversion to a test statistic. So under the null hypothesis, we're assuming that the population mean mu is equal to 5'9". And so when we say that the rejection region is 5'11", what we're doing is we're finding the endpoint 5'11" here. And we're saying if we observe a sample mean greater than 5'11", and notice that's going to result in a small p-value, we would reject the claim that mu is really equal to 5'9". Whereas if we find a sample mean that is less than 5'11", then notice we would have a large p-value. And what we're saying here is we would fail to reject. All right, so let's look at how we would calculate the probability of our type 1 error. So again, alpha is equal to the probability of a type 1 error. And then we're just going to write out the definition of a type 1 error. That occurs when we reject HO, given that the null is true. Well, this is equal to the probability. Notice we're going to reject the null when Y bar is greater than or equal to 5'11". And the null is true when mu is equal to 5'9". Now, to make this easier, instead of looking at feet and inches, I'm just going to convert this over to inches. So notice this is equal to the probability that Y bar is greater than or equal to 71 inches, given that mu is equal to 69 inches. All right. Now, notice what we've got here. We're given that mu is equal to 69. In other words, that tells us which sampling distribution we're looking at. So this is the same thing as mu being equal to 69 in the center. And we're going to find the area in the tail, which corresponds to Y bar being greater than 5'11". In other words, we're finding this area here. So since, notice we had 10 observations in our sample, so we've got Y1 through Y10. Under the null hypothesis, we know that these are all distributed normal with a mean of 69 inches, and we're given a variance of 9 inches. We also know the distribution of Y bar. So we know that y bar is also distributed normal with mean mu. And then remember the variance is going to be equal to sigma divided by n. Or pardon me, sigma squared divided by n. So if I wanted to find alpha, or this probability, what I'm really finding is this. Alpha is going to be equal to the probability, and I'm still interested in the probability that y bar is greater than or equal to 71, given that mu is equal to 69. So what I've got here is that y bar is greater than or equal to 71 under this condition where mu is equal to 69. So what I'm going to do is I'm going to standardize this based off of this distribution. So if I standardize y bar, that's going to be y bar minus the mean, which is 69, divided by the standard deviation, which is the square root of 9 divided by 10. And then if I do that to y bar, I also have to standardize the value of 71. And notice this is equal to the probability. Well, this is now z, because I've standardized it, of z being greater than or equal to 2.1082. And then from here, you could either use your standard normal table, or you could find your calculator to find that area, and I found 0.0174. Notice that this is a small area. So using this cutoff seems reasonable. Now, typically what we will do when we find those rejection region cutoffs is we could do the opposite, and we could set alpha to be equal to 0.05, which is what I was saying earlier, and find the endpoint that corresponds to the area being equal to 0.05. Now, let's calculate beta. Now, in order to calculate beta, recall that beta is the probability of a type 2 error. Now, since beta is equal to the probability of a type 2 error, that is the probability that we accept accept HO, given that HA is true. Now, if we're going to assume that HA is true, remember that the alternative states that mu is bigger than or equal to some value for this example. So we have to pick a specific place in the alternative in order to be able to calculate beta. And we're going to assume that that place is 5 foot 10 inches. So notice converting everything over to inches, based on our cutoff rule, we're going to accept the null when mu is less than when the y bar is less than 71 inches. And then we're assuming this specific place in the alternative, and so notice that 5 foot 10 inches corresponds to 70 inches. And now we're going to do the exact same thing that we did. And so just to make sure, I'm going to write myself a little note here. So note, we had to pick one value from HA. And so this is the value that we chose. All right. So now in this case, we're assuming that mu is equal to 70. So if we assume that mu is equal to 70, we now have, for this example, that y bar is distributed normal 70 with variance 9 divided by 10. So that's where this conditional portion comes into play. Notice what we're doing is we're really shifting the sampling distribution to different places. So if we want to find beta, we find that beta is equal to the probability that y bar is less than 70 divided by the square root of 9 divided by 10, less than, this time, 71 minus 70 divided by the square root of 9 over 10. So that's exactly what we did before. We're standardizing both sides. And you should find this is equal to the probability that z is less than 1.0541, which is equal to 0.8531. Notice this is large. So what this tells us is this means that if mu is equal to 5 foot 10 inches, we will probably make a type 2 error. And we would conclude that HO is true, or we would fail to reject it. And so in other words, what this is telling us is we don't, with a sample size of 10, we don't have a very good chance of detecting mu if it's not very far into the alternative hypothesis. All right, so for this section's quiz, I'd like you to try part C. And I'd like you to do the exact same thing that we did here in part B, and I'd like you at the very end to tell us what this means in terms of this particular test. So we're going to kind of look at a summary of what's going on here. All right, so using this rejection region, which is y bar greater than 5 foot 11, we find that our type 1 error is 0.0174, but beta is equal to 0.8531 when mu is equal to 5 foot 10 inches. And in the quiz portion, you're going to show that beta is equal to 0.1469 when mu is equal to 6 feet. And remember, these values are coming from, we're converting our feet and inches over to just inches. So that's where those values are coming from. So let's kind of draw a picture about what this looks like. So the first thing I'm going to do is just draw a number line here at the bottom. And I'm going to go ahead and mark some different values in inches. So we've got 69, 70, 71, 72, 73. I'm going to go down to 68 over here as well. All right, so remember that under the null, we're assuming that mu is equal to 5 foot 9, which that corresponds to 69 inches. So right here at 69 inches, we have the null value. Right? Now notice we have two different positions in the alternative that we're interested in. They are at 70 and 72. And our rejection region falls at 71 inches. So right here, we've got our rejection region. All right, so we have two different sampling distributions for x bar, or for y bar that we looked at when calculating beta. One of them occurred at mu is equal to 72 inches, so it looks something like this. Forgive my picture here for not being great. So this is one of them, so that's one possibility for being in the alternative. And notice it's in the alternative because we are to the right of the null value. And then the other option occurs here at 70. So here's what my other sampling distribution would look like, and I'm just going to have it fall behind the first one. So if we look at the different areas under the curve, notice for this curve, this is the one that occurs if in the alternative we assume that mu is equal to 72. If we look at the area to the left of the rejection region, we get 0.1469. 0.69. On the other hand, if we look at our other curve, and this is the curve that occurs when mu is equal to 70, if we look at the area to the left of the rejection region for this one, we get 0.8531. So as our distribution under the alternative shifts further into the alternative, we're going to end up with smaller type 2 errors. But if we are in the rejection region very close to the null value, we're going to end up with higher type 2 errors. All right, and so there's another example here that says, suppose we change our rejection region, and I'll let you look over this example on your own. It's just like what we did, except we're shifting our rejection region a little bit. And then down here at the bottom, we've got a summary of what we found for you to read on your own as well. And this is going to conclude the section 10.1 and 10.2 notes.